Okay, we're out here this morning to have a chat about phasors for velocity and for acceleration. And I want to just remind you of the situation that we're talking about a mass on the end of a spring bouncing up and down with constant amplitude, constant period. And last time we worked out that if we want to draw on a phasor for the displacement, starting from the equilibrium position, moving upwards, then we have to draw that displacement phasor like that, out to the right, because phasors rotate anti-clockwise. Therefore, if we model the displacement as a point at the tip of that arrow, then as that phasor rotates anti-clockwise, the vertical position of the tip of that arrow is going to model what the mass is doing. We can also draw phasors for what the velocity and what the acceleration of that body are doing. So at that point there, when it's at equilibrium position and heading upwards, what do we know about velocity? We know that the direction of the velocity is upwards because it's heading upwards, and we know that at equilibrium position, that's where the velocity is the maximum. And so, in fact, our velocity phasor is going to be directed straight up, like that. And they're not to the same scale, right? Velocity is not measured in the same unit as displacement. Really important to remember that they are working on different units. Therefore, even though we can draw those arrows on the same diagram, we can't add them together or anything because they're not measuring the same quantity. We can work out the length of that velocity phasor because we know that there's an equation for moving between rotational motion and linear motion, and we're trying to model the instantaneous velocity of a point on the circumference of the circle, and so we can use the equation V is r omega. And how big's the radius of that circle? Well, it's the same as the size of the displacement, which is equal to the amplitude. And so the length of our velocity phasor is a omega. The length of our displacement phasor, you might remember, is just a, the amplitude of motion. And so now we're going to think about the acceleration phasor. So what's the acceleration doing when we're at that point there? Well, the acceleration, we know, depends on the size of the displacement, and it's in the opposite direction to the displacement. So, as that displacement arrow twists upwards to be positive, we're expecting the acceleration to be the opposite, negative. And the way we can make that happen is having the acceleration phasor 180 degrees out of phase with the displacement phasor. In other words, the acceleration phasor is going to be pointing over there. And that makes sense because we expect that at equilibrium position, the acceleration is going to be 0, but as that mass moves above the equilibrium position, the further it moves above the equilibrium position, the greater the acceleration is going to be, and directed in the opposite direction. So, that's where we locate our acceleration phasor. And how big is that phasor? It's not the same unit as displacement or velocity, it's acceleration. Acceleration, circular motion. Oh yeah, A is V squared over R. V squared. We already know that V is R omega, so A must be R omega squared over R, and with a little bit of rearranging, you'll work out that that's r omega squared, except how much is the radius of the circle? It's equal to the amplitude of the motion. And so the length of our acceleration phasor is A omega squared. A little side note, there are equations that people publish for these which are a waste of our time because they frequently give us the wrong answer because our calculators are only good at finding the position on a trigger graph that's closest to the origin, and often that fact means that the equations don't give us the right answer. They give us an answer but not the answer we're looking for. Nevertheless, we can look at these and we might remember from last time that the equation for displacement was a sin omega t. Remembering that omega t is just the angle that the phasor has twisted in a certain time, because omega is the angular frequency and t is the time. The velocity phasor we frequently see written as a omega cos omega t, and that makes sense because cos graph starts from maximum value and descends to 0 after 90 degrees, which is exactly what that's going to do. And finally, acceleration we see written as minus a omega squared sin omega t, and that makes sense because the a1 is doing exactly the same as what the y1 is, except that it's going in the opposite direction, so it's a minus sine 1. Also important to note is that the velocity always leads the displacement by 90 degrees, and the acceleration always leads the velocity by 90 degrees, which means that the acceleration and the displacement are always 90 degrees out of phase. Now, some of you will like to play spot the difference, and so we're going to play spot the difference between acceleration and displacement. Gosh, those are quite similar, aren't they? Look, they've both got a sin omega t. Sin omega t. They've both got an a. It's only the minus and the omega squared. That's different. Let's write that down. So the a1, a, is just equal to the y1 with a minus omega squared. Except we normally write that the other way round. We normally write omega squared y. And that is a critical equation for our simple harmonic motion, because you might remember right back to the first principles of simple harmonic motion that a equals minus ky, which told us that the acceleration, the size of the acceleration, depends on the size of the displacement. It's in the opposite direction, and k is just some number. Well, we've just managed to shine some light on k, and that is that k is equal to omega squared. This is really useful because we know that omega is the angular frequency. Omega is 2 pi t. Suddenly, we've got a t in our equation, the period of motion. Suddenly, we've got a way of working out the period of our motion, because the omega is 2 pi over t, or it's 2 pi f. We're going to use that next time to write down equations for the period of a pendulum, the period of a mass on a spring, things like that. Okay, so here goes an example of how we can use phasors to help solve problems. For instance, we've got a physicist swinging on a swing, amplitude of motion 4 meters, period of motion 5 seconds. They want to let go of that swing so that they can just walk away from it. Walking speed, 1 meter per second. We want to know at which point should they release the swing in order to be moving at walking speed. Well, we've got a tricky one because they're at the moment at the amplitude position, and so we're going to have to start by drawing a phasor diagram and drawing on our phasors. If you want to do this yourself, pause the video now, draw a phasor diagram and draw on phasors for displacement, velocity and acceleration at that point. That's negative displacement. Okay, so hopefully you got those three phasors drawn on. We've got the A is equal to the displacement, and that's pointed down, negative. Negative because the displacement is to the left, and left is negative, right is positive. The velocity phasor at 0, because at the amplitude of motion, velocity is 0, but it's about to go positive. And the acceleration is at a positive because it's pointed to the right at the moment, and it's a maximum. Next step, work out the angular frequency. You can do that yourself. Pause the video and do it now. I'm going to leave my angular frequency with a pi in it for the moment. That's going to hopefully make my working a little bit nicer and neater. Because of pi being an irrational number, as soon as we put in the pi button on our calculator, we're just going to fill up the screen with numbers and make things complicated. So my advice is leave the pi in there as a pi. We want to know where to let go to be moving at exactly 1 meter per second. So we're going to start by working out the length of that velocity vector. So hopefully we got 8 pi over 5. And 8 pi over 5, it's probably not a bad time to take the 8 pi over 5 and turn that into an irrational number. We know that it's going to be around about 4 or 5-ish, but we can work out exactly what it is now. 5.03. And so the next step is to redraw the velocity at a point where it's going to be approximately equal to 1. And in fact, if you're an on-to-it physicist, you will have noticed that there are in fact 4 different points where the velocity is going to be equal to 1. The length of that velocity phasor is 5. The radius of the circle, as far as the velocity is concerned, is 5, and therefore 1/5 of the way up to the radius point is going to be 1 meter. And 1/5 down is going to be -1. And so the 4 places the velocity phasor could be, any of those points there, the speed is going to be 1. But because the question wasn't clear, we're just going to go for the next place where it's exactly 1 meter, which is going to be that one just there. So let's get rid of the complexity. So we know that the length of that velocity phasor is 5.03, and that the velocity wants to be 1, therefore we can draw that triangle there and work out the angle. The angle we can just use sine. And I got 0.198 radians. We know that the phasors are always 90 degrees apart, and so we know that the displacement phasor is going to have rotated through that same 0.19 radians. The displacement phasor is going to be exactly there. And so we can see that the same angle can be drawn on like that, and we're trying to find the displacement at that point. And so we've got the hypotenuse, we're trying to find the adjacent, we can just use the cos. And we should have got 3.92 meters. In fact, they've only moved 8 centimeters from the amplitude point, and they're ready to let go. That's how we can use phasors to help solve problems. Find one, find the angle, find the other.